but not my final lecture. So there are two more. Semi-final. So there is a competition. Okay. Last time I tried to motivate in great detail and at great length how you should compactify moduli of abelian varieties. So we discussed admissible covers that you should keep somewhere in the back of your mind, but they're not related to what we're going to do now. And then I computed for you modulo some questions that hopefully you resolved by yourselves. If not, you should ask me. It's Jacobian of an irreducible nodal curve. And that guides us, should guide us, on how we should compactify the moduli space of abelian varieties. But if you were not there, like some distinguished members of the audience, you should forget it. And I'll tell you what the degenerations of abelian varieties are anyway. So we'll do this for a while, and then we'll move on. So this is about degenerations of abelian varieties. And what I really want to do is I want to compactify AG. And I have to admit that given the timing and how much, well, more precisely how little time I have left, I think the focus of this and remaining lecture will be heavily on AG, where I'll try to prove something for you, and then I'll say that some things like this may possibly work for MG. So this will be our guide. Recall that the moduli space of abelian varieties, and I will probably be sloppy. Whenever I write this or this, I mean exactly the same thing. I will never bother talking carefully about the stack versus the coarse moduli space. So usually people write one of these for the coarse space, one for the stack. I mean the same thing. I might be writing the other ones. So the moduli space of complex, principally polarized abelian varieties, and I will never again say the words complex, principally polarized. I'll just say abelian varieties. That's what I mean. Recall that this is a quotient of the Siegel upper half space by the symplectic group, where HG, recall, was a set of G by G matrices, as complex entries, which are symmetric and which have positive definite imaginary part. And my goal is to compactify this. This is a quotient of that. So if I could compactify this in such a way that the group action would extend, the quotient would give me a compactification here. This is very optimistic. I don't really need to compactify this. I could be able to add just a bunch of points here so that the quotient would still exist, and I would get a compactification. So let me get back to our usual example, genus 1. So A1 is the quotient of the upper half plane by SL2Z. And A1 bar, this is A1 union 1 point, and we have discussed that somehow I should think of this point as being I infinity. And if I want to write it as a quotient of something by SL2Z, you can ask yourself, what should I add to H? And if you think of the upper half plane, it's very clear how to compactify the upper half plane. You just add the line at the bottom and the point at infinity. Remember, there is a vertical direction of the upper half plane. But if I were to try to write here union R, union the point I infinity, this is not a good idea, because if you look at the action on R, you will see that I'll get many, many orbits. So I'm not adding 1 point, I'm adding many points. So this is bad. So what you do instead, you look at I infinity and you look at its orbit on the SL, and this is Q. And now I have written a correct statement. So if I take the upper half plane, add all the rational numbers, and add 1 point, which I'm labeling as I infinity because I'm thinking of it as the top, then these all together form one orbit of SL2Z. So the action extends, and the quotient certainly adds 1 point, and the topology is correct. You note, of course, that this space is not compact. Okay? And I have not added R. And this is our motivation for what should happen in general. So my goal is I'll try to explain to you how AG is compactified. And to this end, I'll add points here. And I won't compactify this. I'll add things. Unfortunately, I won't define a compactification for you, but I'll try to explain how it arises. And then I'll say what is known about compactifications. So goal I would need to define, presumably, whatever I do, a limit as t goes to infinity of abelian varieties, of abelian varieties A sub tau t, where the period matrix tau t has one entry that diverges to infinity. Okay, t less than r plus. Okay, so this is I have written a G by G period matrix. This is one number. So this guy here is a G minus 1 by a G minus 1 matrix. And you can check that it has to lie in the Siegel space of dimension 1 less. The period matrix is symmetric. So this vector and this covector are the same. Okay? And this guy diverges to infinity. And if I promise that I'm compactifying AG, I better tell you what the limit of this family is. Okay? And you look at this and you can try to think what you should define this object to be. So choice 1, you say that the limit is tau. A sub tau. So let me write tau is the limit of this. Okay? So I'm going to be very sloppy about going from the moduli space of abelian varieties to the Siegel space, because I won't be able to do this properly. So what you're saying here is, I would like to keep track of this, but I can't, because this goes off to infinity. This makes no sense. So I'll just drop all of this stuff, and I'll keep this. In the genus 1 case, you keep nothing. It's okay. It's just a point. There is no objection to doing this. You can do that. That allows you to compactify things. Then, if I want to consider the limit as T1 and T2 go to infinity of a matrix where I have two entries divergent to infinity, I should declare this to be tau again, right? Because if this is my approach, you know, I've done this and then I do the same thing again, so I should be declaring this limit to be tau. Okay? You see why I'm very reluctant to write A sub tau here, because I mean, if this is a limit of G-dimensional abelian variety, this is a G minus 2-dimensional abelian variety, makes no sense. But if I'm thinking of this as a Siegel space, and I'm not worried about any universal family here of abelian varieties, there is no reason why I should not allow myself to do that. In genus 1, I can do anything I want. It will always work. More generally, of course, you can try to do this. So you look at your period matrix, and you take the part of the period matrix that you no longer like in the limit, you throw it out, and you keep the rest. So what does it mean you no longer like the part of the period matrix? So the period matrix is a matrix. The symmetric part of the condition, it's a closed condition, doesn't go anywhere in the limit. So the possible reasons, the Siegel upper half space is non-compact, there are two reasons. I can take the entries out to infinity, which is what I've been doing here, or you can be taking the imaginary part and letting it be not positive definite, but semi-positive definite. And then you take the part of your period matrix where there is a kernel of the imaginary part of the period matrix, you throw it out, you throw out all the infinities in the limit, you keep the rest. So as a result, what you get, so-called Satake, it's usually called Satake, Bailey, Burrell, depending on who you ask, compactification. AG Satake, which as a set is very simple to describe. You take AG, then for these guys, I have just taken a period matrix of dimension 1 less. So it's an abelian variety of dimension 1 less. Here it's an abelian variety of dimension 2 less. And I keep going. So this is a Satake compactification that I have written down as a set, right? If you want to know that it has any kind of reasonable scheme structure, you need an argument that tells you can glue these things together. And this is why it's called a Satake compactification. Satake has proven this. And the reason it's called Satake-Bailey-Borel compactification is that in much more generality for general locally symmetric domains, not just this type, I don't want to say what this means, there is a theorem of Bailey and Borel which says AG Satake is a projective variety. From now on, whenever I write variety, I mean a stack, and this is an issue I will completely ignore. Okay? We don't want to go there. You had a wonderful introduction to Deligne-Mumford stacks. Formality, this is the case. The important thing to know is that this is very singular. And it's not a fine moduli space. Which is to say there exists no universal family. Is this line still visible? Yeah? Okay. So why is it very singular? Well, I have this thing here has dimension equal to the dimension of the space of G by G symmetric matrices, which is G times G plus 1 over 2. The next thing has codimension G. So the boundary of the Satake compactification has complex codimension G. Doesn't say it's singular, but when you see it is indeed very singular. I'm dropping lots of data, I'm forgetting everything. Many different sequences have the same limit. Not a good idea. I mean, not a bad idea, but certainly I don't get any nice moduli space. And the boundary objects have no geometric interpretation. I cannot put any family, because the only family I could try to put would put an abelian variety of dimension 1 less here. And of course, you cannot drop dimension in any kind of reasonable family. Okay? So this is a good compactification for many reasons, but this is not the only choice. And if you think about what we did last time, certainly the C star extension of an abelian variety of dimension 1 less that I wrote as a Jacobian of an irreducible nodal curve doesn't fit in this picture. Okay? So we'd like something else. Proving the theorem takes some significant amount of effort. It's not trivial. I would have to try to describe for you the local structure near the boundary in great detail. It's doable. Maybe in an hour or two it's doable, but we don't want to go there. This is non-trivial. The problem with the second choice of how you compactify is here I have been able to write such a nice formula for the compactification as a set. This will not be the case for what I do now, but I'll get a better behaved situation. So the choice number 2 is for such a family, I'll say that the pair tau and beta is the limit of such a family. So tau t is this family here. Okay? So what does this mean? This means I have done the least damage I could think of. This certainly goes off to infinity, gives me no further information. I cannot keep track of it in any reasonable way. So I kept track of everything else I could possibly imagine. Okay? So where do these guys live? Well, this, as we discussed before, was an abelian variety of dimension 1 less. Well, maybe in the Siegel space of dimension 1 less, if you wish. Where does B live? Well, B is a complex vector of dimension G minus 1, right? So I can think of B as lying here. This is certainly okay if I'm taking limits in the Siegel space. Of course, what I really want, I want limits in the moduli space for abelian varieties. So this means for abelian varieties, I take the moduli space for abelian varieties of dimension G, and you see that this is an abelian variety of dimension G minus 1, and this is a vector in G minus 1 dimensional space, which is actually only defined up to adding periods of this abelian variety. So this is the universal family of dimension G minus 1, so notation. And I'll stick to this notation from now on. is the universal family of principally polarized abelian varieties. So what I mean by this is that the fiber over a class of an abelian variety is an abelian variety itself. Okay? I somehow have done something which is horrible for people who do moduli theory. I just introduced notation. I didn't say this is a major theorem that such a thing exists, right? If you are doing some moduli theory, knowing that you have a universal family is hard. Why is it not so hard? The reason it's not so hard here is I can write down what this is. So, xg is simply the quotient of the Ziegel upper half space times c to the g by the action where on one side I act by the symplectic group, which didn't go anywhere, which now acts non-trivially here also, and then I add by z to the 2g, and this quotient is the lattice given here, and this is semi-direct in some direction, and I always write it in the wrong direction. Okay? So this is explicit. The same way as I didn't really have to worry here about all the stacky business for AG, this is an explicit quotient. This is the quotient of a manifold by a group. The moment I check that the stabilizer of any point is finite, this is a very nice quotient. The same here. This is a quotient of a manifold by a slightly more complicated countable group. If I check that the stabilizer of every point is finite, this is as good an orbifold as they come. It has a universal manifold cover of infinite degree, but still, it's good enough. Okay? So this is why I can just say this is a notation, and this is not a hard theorem to prove. Okay? If you want to interpret this carefully, you have to be careful. I mean, this is about orbifolds. Okay? Yes?
What is the link between B and xg minus 1?
What is the link here? So a point here is tau and b, where tau is the abelian variety corresponding to the tau, and b lies on this abelian variety. Okay, so here I should write curly a. So if I look at this pair gives me a point in here, right? In dimension 1 less, which I can interpret as a point in here. So if I look at the, so I'm trying to add, so what I did is I took the Ziegel upper half space, I added to it a boundary component of this form, right? So I'm adding to the Ziegel upper half space a product of these two things, right? So this whole thing lies on here, right? But this is the universal cover of the universal family of dimension 1 less. Okay? Given such a family, I define the limit of such a family to be the pair tau and b, which is an element in this product. So what is this quotient? I mean, this quotient here is the moduli space of abelian variety. This point here is a point on c to the g. The point c to the g is the universal cover of your abelian variety. So given a point here, I can interpret it as a point on the corresponding abelian variety. So this point here I'm interpreting as a point on the abelian variety. If I wanted to make formal what I just said, I would have to compute the stabilizer. I would have to put infinity here, and I would have to compute the stabilizer of such a matrix with infinity within the SL2Z, SP2GZ, and then I would have to see how it acts on B. And this will be precisely this Z to the G that will remain. Is this clear? No. So I'm trying to define, my goal is to define a compactification of AG. The way I do this is I'll add extra boundary strata to the Ziegel upper half space in a rather explicit way. I mean, I will fail shortly, so I'll add the first boundary stratum here. And then I will say what this corresponds to in terms of the moduli space for abelian varieties. So I have decided to declare, motivated by what we were doing last time, if you'll think about it in a second, that a limit of this family, where this goes to infinity, is such a pair. This gives me a way to attach this locus to the Ziegel upper half space. I attach this locus to the Ziegel upper half space. So this thing here is a quotient of the Ziegel upper half space union one of these loci quotient sp2gz. Okay? I mean, I feel bad about this equality. I need to add many copies of this guy for the group to actually act, right? I have told you how to add one copy of this to here. This is a procedure. I just attach such a point as a limit of such a family. So this gives me, you can check a topological space. The SP action extends if I add many more copies. But in any case, I can see how SP acts here. And if I just take this quotient, I'll get this. Okay. So I have geometrical, I have added the universal family of dimension 1 less, and to be honest, I have to take a quotient by plus minus 1. Because a generic abelian variety has an involution plus minus 1, and that's how it manifests itself. I should take a quotient. Okay. I'll pretend to ignore this plus minus 1. Okay. So I have not yet compactified, of course, right? Because I have only added something, I should allow further limits. So what should the limit of the next family be? X, X. Okay. So again, I'm trying to work so far on the Ziegel upper half space. I will fail by the end of this blackboard, and then I'll tell you what actually needs to be done. But this will tell us why I'll fail. So I would like to define a limit of this, right? Because this is also a family in the Ziegel upper half space, and I would like to say that the limit of this is something interesting, right? And what interesting thing could it be? Well, I should be trying to keep track of as much data as I can. So I certainly should take tau, B1 and B2, right? And if I think of this, I should think of tau giving me a point in the modular space of abelian varieties of dimension g minus 2. And B1 and B2 I should think of as giving me points in the abelian variety corresponding to this tau, similarly to the way that this B here, I would like to think of as a point in the abelian variety corresponding to tau. So I'll try to write curly A for the modular space. Okay? And then the question is, what is X? Okay? So I can just declare that the limit of this is such a triple. This is fine, you would think, but the codimension of such limits, if I want a nice smooth modular space, should be 2. I have allowed 2 things to degenerate. And this means I should keep track of this. And it's absolutely unclear how to keep track of this. Okay? So I need to keep track of it somehow. Okay? And what does this mean that I keep track of X? You see, the problem is that if this is a family when both T1 and T2 go to infinity, there is a large stabilizer of this that somehow maps this family to more or less itself and messes up X in a bad way. So it will be very hard for me to keep track of X in such a way that this is preserved under the group action. Okay? And this turns out to be the problem. So the locus I should add, well, we should add, we're doing this together, right? We should add to AG to encode such degenerations is actually a C star bundle over the coequalizer, the fiber product of this. Yeah, sorry, Melanie, I couldn't resist. So over this guy. Okay. So the triple, tau B1, B2 is an abelian variety with a pair of points. So tau sits in here, tau B1 sits in here, tau B2 sits in here, and the definition of a fiber product is to say that tau B1, B2 is what sits in here. Okay? And the X is encoded by this C star data. Okay? So this is what I'm adding. So the next locus here will be the C star over X G minus 2 squared, and there is some group action here that I didn't bother to write out. It gets messy. Let's try to understand why we might be happier with it. I haven't continued. I have not constructed a complexification, I know. But let me try to convince you that maybe that's a good idea, that what we're doing. So, question. Is there a chance to get a universal family, to get a fine moduli space? So, i.e., does the first stratum, say X G minus 1, parameterize geometric degenerations of abelian varieties? So the question I'm asking, given a tau and b, which sits in here, up to plus minus 1, never mind, can I tell you a compactification as some kind of geometric degeneration of an abelian variety? And the answer is yes. Remember last time we decided, hopefully you believe me, or hopefully at least you still remember that I claimed this, that a Jacobian of an irreducible nodal curve is a compactification of a semi-abelian variety like that. So such extensions, let's call this a tau for good measure, of a tau, what are they parametrized by? So you can view this in two ways. You can view this as either as group extensions, and then you remember your algebra well, and you write suitable X of something by something. Okay? Or you can think that the way I'd like to think about the C star, this actually looks like a line bundle with a zero section removed, right? So these things are parametrized by line bundles on an abelian variety. This is the principally polarized abelian variety. I never said that. This means that it's dual to itself, which means its pk is equal to itself. So they're parameterized by the pk group of the abelian variety, which luckily is just itself because it's principally polarized. Okay? And my B precisely is a point in here. So this means I can interpret now a pair tau and B as an abelian variety of dimension 1 less, together with a data of, well, a line bundle on it, which gives me a C star extension. This is great news, because this means that somehow from this very naive approach I have recovered the data that allows me to parameterize semi-abelian varieties, which tells me that there is some chance that if I succeed further in compactifying, maybe I'll get a fine moduli space. At least it tells me that over this partial compactification, there is a universal family. Okay? I swept many things under the rug. I mean, I need to compactify this to a P1 bundle, glue. We're not doing anything like that. But this tells you you're in good shape. Okay, so with this motivation, let's take a deep breath and let's try to think about compactifying further. So the question is how to actually compactify, how to construct a G bar, which includes whatever we constructed so far. So I want a general story that will tell me how to compactify. And it turns out that the approach that I was so happily, naively exploiting, doing this and taking stuff to infinity, is not the right approach. So should, in fact, add components, add to HG various strata where the imaginary part of tau is only semi-positive definite, okay? Which means it's not positive definite, it has a kernel. You can easily check that actually going off to infinity is not needed. You can take an action of the symplectic group that sends infinity to 0, basically, and this means that any degeneration of this sort I should be able to interpret equivalently as one of the entries of the period matrix going to 0, okay? I didn't do it because pedagogically I chose to do what I showed you because it tells you very vividly how it works. This is the correct approach, because if you're starting to go off to infinity, you have 4 different infinities in the period matrix and you need to compare the rates at which they go to infinity, and that gets messy. It does not work. Okay? So, theorem. There exist many toroidal compactifications of AG such that their strata are toric variety bundles over fiber-wise products of the kind we had. Okay. And this parameterize these guys parameterize extensions of this sort. So if I want to have an extension of this sort, that's precisely the data I need. This is a bunch of line bundles. Each line bundle is given by a point, so I need to choose a bunch of points. So what is the toric variety business? The toric variety business corresponds to this X that we have never decided how to keep track of. And what this X does, it tells you nothing about this extension, but it tells you how to compactify this extension to what I called the semi-abelic variety last time. So last time I said that this needs to be compactified to a P1. There is not so much choice on how you compactify C star to a P1. It's much more interesting to try to compactify C star squared to P1 squared, because then you have to somehow to glue the different sides. And on P1, it's very easy to identify 0 and infinity. You identify 0 and infinity. On P1 squared, you want to identify the 0 section in one direction with the infinity section in the other direction. And these are each a copy of P1. And you're identifying them with multiplication precisely by this x. This is the role that x plays. So the storic variety is somehow a glue-in data for compactifications of this. Okay. And I'm afraid that's all I can say about how this works, but let me tell you something. So let me tell you what kind of input you need. So this says there exist many toroidal compactifications. Of course, you're not supposed to state theorems like that, but still. This is a work of many people. I think the first place where it appears is a book of Ash, Mumford, Rappaport, and Ty. Has been generalized greatly in various directions. There is much work and so on. So let me tell you what data is needed to define a toroidal compactification. So data needed to define a toroidal compactification. So let CQ GR be the cone in sim2 of RG consisting of semi-positive definite matrices M such that the kernel of M has a basis of rational vectors. Sorry, I mean, there is no way around this, and I at least need to tell you what data is needed. So this is called the cone of semi-positive definite matrices with a rational radical. Rational radical means this. Okay? So you want symmetric G by G matrices, which you think of as quadratic forms on the reals. You want them to be semi-positive definite, so it means that if you plug in any vector v and itself into this, you'll get greater than or equal to 0. And then there is a kernel, those things where the thing is 0. And you want this kernel to have a rational basis, a basis consisting of rational vectors. This corresponds in genus 1 to the fact that I didn't want to add all of R to the upper half plane. I only wanted to add Q. So this rational business is this Q versus R business. Then data for a toroidal compactification is the decomposition of this guy into polyhedral rational cones invariant under GLG Z. Okay, so what does it mean, a polyhedral cone? So it means a cone that's generated by finitely many vectors. Not every cone. A cone just means that it has the vertex, and given any point, the entire array starting from the vertex and going to this point is contained as the cone. Of course, not every cone is polyhedral. In particular,
by cone you mean a closed convex cone?
so this guy I defined. When I say polyhedral cone, I mean this is a definition of a cone, right? This is a cone in the sense that if I take any element in here and multiply it by a positive rational number, it stays in here. The kernel didn't change. When I say here cone, I just mean, this thing. So you have a bunch of vectors and you take r greater than or equal to 0 of them. I'll do a couple examples now, but there was some question before. No? Oh, convex, sorry. Oh, sorry. Yeah, I didn't realize that. Yes, convex should be here. Sorry. Sorry, Olivia, I didn't, so convex has to be here. And when I say decomposition, I'm glossing over many things. So it really should be a decomposition. It means every point of this guy should lie in some cone. The cones should intersect only on their faces. I should really count the faces as parts of the decomposition. So, this all goes for me under the name decomposition. Okay? This is tough. Let me do examples. G equal to 1. We should start with that, right? We always start with that. That should not be tough. So what is this cone of 1 by 1 semi-positive definite matrices with a rational kernel? That's a fancy name for r greater than or equal to 0. Right? It's one number, and it has to be semi-positive definite, which means non-negative. And if it's 0, it's 0. The kernel is anything, the irrational condition is boring, right? So the cone decomposition, so this is r greater than or equal to 0 of vector 1, right? Of matrix 1, of 1 by 1 matrix 1. And there is really no other cone decomposition, right? So it's sort of unique. You can rescale this, but this makes no difference to the cone decomposition. Okay? So there is no choice, which is good because somehow if there was a choice here, I should be telling you that A1 has different compactifications, which does not look like likely to be the case. Okay? So this is good. G equal 2, this is more interesting. So these are matrices A, B, B, C in 2 by 2 matrices, which are semi-positive definite. So this, if you recall the condition for being semi-positive definite, you can check the diagonal minus whatever this is called. So the A is greater than or equal to 0, and AC minus B squared is greater than or equal to 0. And then I'll write with rational radical here, and this means whatever it means. We can figure it out, but I don't want to spell it out. Is this too small? Is it visible? Somebody reliable in the back. Scott, can you still see it? Too small. Okay. I can write smaller, it's okay. Okay. Okay, now it's hopefully visible. Yeah? Better? Okay, so this is what it is. And notice, of course, if I take A, B, and C and multiply them all by a non-negative real vector, I stay in the same space. So this is a cone. But this is not a polyhedral cone, right? This is like circle. If I were to cut it, I'll see a circle. Okay? This is a cone in a three-dimensional space, And this is the limit of my abilities to try to draw, right? So sim2 of R2 is already three-dimensional. So I can draw this guy, and I'll draw this and say, this is what it looks like, and this is true, right? In genus 3, there is no chance I'll draw anything for you because I cannot draw a cone in 6 dimensions. Okay? So this will be the end of my drawing, but I'll tell you something useful. So I would like to decompose this into polyhedral cones, and now I have to do some work. I cannot just say take the whole cone. It's not polyhedral. So there needs to be a decomposition. So theorem, proposition, and this is a combinatorial theorem, and you can just prove it by hand, that let sigma be the following cone. So now you will see what I mean by a cone, by a polyhedral convex cone. I ran out of space, sorry, the proposition continues around the blackboard. Okay, and then the union of a gamma in GL2Z of gamma, this is the entire, whatever my notation was, CQ2R. Okay, what does this say? This says that if I take this particular cone and all of its GL2 conjugates, I get precisely the cone of 2 by 2 real semi-positive definite matrices with rational radical. Okay? This requires a proof. I have to prove, first of all, that all the orbit, this requires a proof that any such matrix can be conjugated by an element of GL2Z to this cone. Then, if I want this to be a decomposition, I also need to check that GL2Z translates of this cone don't intersect, right? That they really give me a decomposition, that they don't slice each other any further. This is also true. And theorem is this defines A2 bar, and any toroidal compactification of A2 is obtained by a further subdivision, by a subdivision of this sigma. So any toroidal compactification is actually a blow-up of this particular one. Okay? So subdividing the cones, I asked for a decomposition here. And of course, you can take any cone and just slice it in two. And this will define a different toroidal compactification, which will just be a blow-up, in fact. So what this tells you is that essentially there is a unique reasonable compactification A2 bar of A2. Okay? I cannot prove this here, but this is a very direct combinatorial thing. There is a field of study called quadratic forms. For them, this is, exercise 0.0, something like that. So you can prove this. Okay, no more drawing finally, and not so much more time, so let me continue. So G equals 3. So let sigma be defined the same way. The same way, I mean, I'll just permute all the coordinates. Okay? So I'll write 3 of these guys and 3 of these guys, so there are 6 generators. So this is a cone in the space of, I mean, these are clearly semi-positive definite. The sum of semi-positive definite matrices is a semi-positive definite matrix. So this is a cone in the space of semi-positive definite matrices. Let's not worry too much about the rational radical. It's true. This is something I don't want to explain. And the same holds. So there exists unique minimal A3 bar. Okay? So this is to say that if I take this cone and this GL3Z orbits, they cover the entire cone of semi-positive definite symmetric matrices with rational radical, and that every other subdivision is obtained by slicing this cone further. Okay? That was very easy. You don't see any reason why we need to suffer. So now let's suffer. G equal 4. I should be doing the same, right? Let sigma is equal to R greater than or equal to 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, plus okay. This is still a cone. This is a full dimensional cone, so this is 10 dimensional inside the full thing, which is also 10 dimensional. So you have a 10-dimensional cone of these things, right? And you have inside it a 10-dimensional polyhedral cone. And now I would be delighted to write the same holes. In fact, if I take the union of all gamma in GL4Z, gamma sigma, this is contained, of course, in this cone. No doubt about that. Acting by GL doesn't change any of the conditions, but this is not equal to it. Okay? So what does it say in terms of quadratic forms? It says that I can write down for you on the blackboard, and I don't have it in my notes, but I could write down. It's very simple. A 4x4 rational symmetric, real symmetric matrix, which is actually positive definite, and the difference is a 10-dimensional thing. So I can write down a 4x4 positive definite real symmetric matrix, which cannot be conjugated into an interior of this cone. So this means that if I just write down this cone, I have not yet told you a decomposition of this, and this means I have not yet told you a compactification of A4. Okay? So in general, there exist many different, and I really mean different, toroidal compactifications of AG. Okay? Maybe I should apologize here for just writing a sequence of facts with no motivation. And the problem is I don't have any motivation. So there is no hand-waving way for me to convince you that this is still okay, but this fails. Let me tell you, just so that you are warned, that your intuition, if you have never thought about the things about polyhedral cones, is wrong. I don't know what it is, but it's wrong. Mine is also wrong. So for example, you think of a cone probably like something like that, right? Yeah, or something like that. Okay, so this is fine, but I mean there are these cones that are not simplicial, so somehow there is 12 vectors in a 10-dimensional space and they span something big, and you slice them, and it's not clear that you can slice them out so that you get something simplicial immediately. It's hard, right? Our intuition really fails. So somehow if you think about if you take a slice of a polyhedral cone, it's a polyhedron. And polyhedra in high dimensions are complicated combinatorial objects that you should be very careful with. Okay? So by now I've learned that my intuition is wrong, so whenever I want to make a statement about this, I prove it. Okay? And that works. But just be very careful. So in particular, these toroidal compactifications are non-smooth in general, and this corresponds exactly to these non-simplicial cones. And there is all sorts of bad luck here. But let me tell you something that I can tell you here. And this is that there is a toroidal compactification that we'll spend 1 hour later today dealing with. And I won't be able to define it for you, as you have probably figured out by now. And I won't even tell you what the subdivision is, right? To tell you a toroidal compactification, I'm supposed to write down for you a decomposition of this into some cones, right? And I'm supposed to write down the cones for you, and I won't do that, because that's a serious combinatorial definition that takes, half of this long blackboard to just state and another hour to explain. But let me tell you what is known. Fact: there is a so-called perfect fan decomposition of this for any genus, such that the corresponding toroidal compactification A G perf satisfies the following list of properties. So part 0, which is actually true for any toroidal compactification, is that there exists a contracting morphism to the Satake compactification. Okay, the Satake was this explicitly described thing in the beginning, and actually any toroidal compactification admits a contraction to the Satake. If you think about how I was defining this, I was playing with more and more data, but the original data needed for the Satake was always there. So I can just forget all the fancy stuff and keep the Satake data. Yeah. So this is not anything special about the perfect cone toroidal compactification. All toroidal compactifications have this. I just want to tell you this, and I'm telling you this now. Something special about the toroidal compactification is the following, is that for any I, the codimension in the perfect cone toroidal compactification of the preimage of A G minus I inside here has codimension I. Okay? So this thing, remember, this is AG union AG minus 1, union AG minus 2, and so on. So this naturally defines me a stratification of this guy by torus rank, if you think about it. Okay? And the way it looked like, the way I was trying to define things, this should be true for all toroidal compactifications in my naive approach. This is absolutely false. This is why you should really define toroidal compactifications. This fails miserably for other toroidal compactifications. There is a wonderful compactification called second Voronoi toroidal compactification, which keeps having boundary divisors deeper and deeper and deeper. Okay, so this is very special to the perfect cone toroidal compactification. I won't be able to prove it for you, of course, because I won't be able to define this for you in the first place. Some more properties. The boundary of this guy is an irreducible divisor, which of course is then the closure of the preimage of AG minus 1 here. So the boundary is everything, right? But the boundary is irreducible. Third, this guy is singular, but has canonical singularities. hopefully you remember Paolo's lectures and the discussion about types of singularities. So what I care about is that the canonical class makes sense. Okay. Okay. So these were somehow properties of the perfect cone toroidal complexification. I know I'm over time. I'll take 2 minutes to try to convince you that even though I haven't defined this object for you, it's reasonably natural for various problems, not for all. So this is, by the way, a theorem of Tye, later corrected by Shepard-Barron. This is a theorem of Shepard-Barron. Which says that AG perf is the canonical model for AG for G at least 12. So canonical model in terms of the minimal model program, and what this means really is that he proves that the canonical class is ample for G at least 12. Okay. 5. So this is somehow a natural complexification for the minimal model program. 5, my motivation, if you recall, was to try to extend the Torelli map, and the Torelli map extends. So the Torelli map extends from mg bar to the perfect cone complexification, and this is the theorem of Alexeyev and Bruniate. And just to emphasize how difficult these things are, the complexification was constructed, in 1970s essentially. Tye proved that the singularities are canonical in 1981. Shepard-Barron's result is, I think, around 2010 or so, depending on whether you count the publication date or the archive date, and it's about 2015. Okay? And to tell you that we don't yet know everything, is there is no known universal family over AG perf. Okay? It doesn't mean we don't know it doesn't exist. We just don't know if there exists one. There is another complexification called the second Voronoi, which does have a universal family. This holds, this does not hold, this holds, this does not hold, so it's much harder to work with. Okay? So there is this complexification. And I'm already over time, so I'll just take this amount of space to tell you what the remaining 1 hour will be so that you know whether you come back. So goal will be much modest than this. The goal, I'll tell you that the canonical class of AG perf is big for G at least 9. And this is a proof due to Tye. And of course, there'll be a couple of computations that I'll skip along the way and I won't be able to explain to you. But I'll tell you where it comes from. And this is a technique that's not commonly used now for studying birational geometry, but I wanted to do it because I think it may be applicable in other instances where people have not tried. This comes from the original paper of Tye. If you open the paper of Tye, you will see a proof of this statement. What I'll write on the blackboard in a couple hours will have nothing to do with what is written in his paper, but it is his proof just with a modern interpretation. Okay? Big means that this thing is of general type. In terms of Kadara dimension, I don't want to go into this. So big essentially means it's epsilon better than effective. Okay? And that's what I'll prove. Okay, sorry I'm over time. Thank you.